Yes. Hello, everyone. Welcome to the distinguished webinar series in artificial intelligence and cybersecurity as performed by CTSR, University of North Dakota. Today, we have another valuable researcher from Missouri University of Science and Technology, their Dr. Venkata Sriram Siddhardh Nadendla. And before allowing him to share his valuable perceptions and presentation in terms of the EEG-based spiking neural networks and considering the problem of the breaking intent detection on neuromorphic hardware, I'd like to make a general brief introduction for Dr. Nadendla. Dr. Venkata Sriram Siddhardh Nadendla is an assistant professor in the Department of Computer Science at Missouri University of Science and Technology. And prior to joining the Missouri S&T in fall 2018, Dr. Nadendla worked as a postdoctoral research associate in Coordinated Science Laboratory at University of Illinois at Urbana-Champaign since October 2016. He received his PhD degree in electrical and computer engineering from Syracuse University in 2016 and his Master of Science degree in electrical engineering from Louisiana State University in 2009 and his BE degree in electronics and computer engineering in 2007 from SCSVMV University, India. He also worked as a research intern at ANDRO Computational Solutions LLC, Rome, New York in the summers of 2013 and 2014. His research interests broadly span the field of trustworthy cyber-physical human systems with special focus on machine learning, game theory, security, algorithmic fairness, networks, and statistical signal processing. In recognition of his research, he received 2 Best Paper Awards in SMARTCOMP 2019 and SMARTCOMP 2024. Dear doctor, after that, the biography is all up to you. You may start sharing your screen, and we'll be listening and considering the valuable feedback in terms of your research. I'm also very interested in, especially that the hardware side of that, all of that biomedical oriented research work. So I'm very interested in especially your the presentation. So welcome, and it's on your side. Yeah.
Thank you, Dr. Kose, and thank you, Dr. Ranganathan, for the warm introduction and the invitation to give this presentation. So let me, okay, for some reason, I'm unable to share my screen. Okay.
I think you are now able to share.
Yes, okay. I am able. Give me a second, and there it is.
Yes, I'm able to see. Probably that attendants are also able to see. Yes, it's on your side. Thank you.
So thank you for this wonderful introduction and the invitation to give a talk on July 4th. It's a special day, so I think I'll take it as a privilege to give a talk on this day, on the Independence Day of United States. So I'm going to talk about my work with a student, Nathan Lutz, and my colleague, Professor Krishnamurthy here at Missouri University of Science and Technology. And this work is titled EEG-based spiking neural networks for breaking intent detection on neuromorphic hardware. So there are a lot of keywords in the title. I'll probably start off from something very basic, and I'll build the talk as we go forward. So to start with, let me go back to one of the fundamental problems that we have in the world of driving, in the world of transportation. So if you see any sort of transportation system in the world, especially road transportation system, you encounter driver inattention, and probably this is because there is inattention due to distraction, due to fatigue, due to various reasons. And the consequence, the impact of this driver inattention is that it can lead to driver fatalities. or very serious injuries. And if you just see one of the recent reports released by the National Center for Statistics and Analysis from NHTSA, most of a good fraction of these accidents that are happening on the road are because of either the influence of alcohol, drug, and medication, which would automatically cause inattention, or it could be because of distraction or drowsiness. So if you actually add up all these numbers together, that accounts to 1/5 of all the fatalities that are out there. And this is just the fatalities. I'm not even talking about the injuries that are caused due to these accidents. So now I think with this one slide, I've established the importance of this particular problem. And what you see here, the table, is extracted out of this report that has data only from the year 2021. So just in the year of 2021, you have roughly about 11,000 accidents due to cognitive inattention or driver inattention. And so it's a very, very important problem that needs to be solved in spite of all the technology that is out there. So let's start with what is out there today. And this technology is called traditional driver assistance. So the idea is, so if you have the vehicle right in the center, there is a circle of safety that we are trying to ensure around the vehicle. And the way in which, so this is the circle of safety that I'm talking about around the vehicle. And the way in which we achieve the circle of safety is through techniques called ADAS, or Advanced Driver Assist Systems, which basically use various types of sensors, different types of sensors, to monitor the surroundings of the vehicle. So to give you a simple example, you can have something as simple as lane departure warning, where if a person is inattentive and the vehicle starts drifting from the lane, the vehicle automatically detects that and gives a warning. Now, if you notice what's happening in these techniques, in all the techniques that are out there in the traditional approaches, they observe the surroundings and they give a warning. Now, a warning or an alert. And these warnings or alerts are irrespective of what the driver's state is. So these methods observe the environment irrespective of what state the driver is in. They give you the alert, the warning, or the intervention. So naturally, the next step was to take into account what the driver's cognitive state is, and which is why we are today in the world of personalized driver assist systems. And what I mean by this is these systems try to learn the driver's cognition or behavior, and they present shared cognitive interventions in a timely manner. So I particularly highlighted the driver cognition behavior learning part here with an underline, because that's what we're going to focus on in the rest of the talk. But there is also another element to this, where once you learn the driver's cognition, you also have to present an intervention accordingly. And I personally have done some work on this. We have a paper that got recently accepted in Transactions Human Machine Systems. I'm not going to talk about that today. I'm going to focus completely on how to learn the driver's cognition or behavior. And there are a lot of early attempts on how to learn driver cognition and behavior. So if you actually study the literature, there is a very nice paper out there which puts all the various papers out there together and gives you a nice survey on this topic. And that's paper number 3, which is cited below. It's not written by our group. It's from Transactions on Intelligent Vehicles. So broadly speaking, you can categorize all these methods out there into 3 different types. One is physiological, which is based on data collected from the driver using physiological sensors. That could be EEG, PPG. So you have all the list of sensors that are out there that are being used in order to collect physiological data of the driver to learn what their cognition state is, what their behavior is. Okay. And then you have the second type of method, which is behavioral. And behavioral methods use not physiological sensors, but external sensors like cameras, that are facing the driver, in which case you're trying to learn whether or not the driver is opening their eyes or closing the eyes. Are they yawning, or are they turning their head, or are they looking at the road? These are the kinds of things that you can learn using camera feeds, and those methods are called broadly behavioral methods. And the third type of method is called vehicle-based, and these vehicle-based methods rely on inputs that are given to the vehicle. So let's say you turn the wheel, and the amount at the rate at which you turn the wheel, or the angle with which you turn the wheel, or the amount of braking that you do, all of those are called are the inputs that are given to these methods, and the methods use them to develop techniques to learn the driver cognition or behavior. Now, of course, once you have three different types of modalities here, you can always combine them and see how they do. And so therefore, there are also hybrid methods too. So technically speaking, all of these different sensing modalities are used to study, broadly speaking, the following problems. You're either trying to study the driver behavior or driver fatigue, whether or not they're drowsy, and is there any intent to do certain action? And so those are the kinds of problems that we are looking at. So what is it that why is this problem challenging? So here is my take on this. The challenging part is that if you rely on vehicle-based methods, so if you just rely on steering wheel rotation or braking pedal inputs, these are, it's very hard to learn what the driver's cognitive state is based on these. Yes, these methods exist, but the performance of these methods are very, very low. Now, on the other hand, if you rely on behavioral methods, often what happens is if you're putting a camera in front of the dashboard, and if you're looking at the driver, most often by the time the driver closes their eyes, they're already very tired, they're not paying attention. So it's quite late. The detection methodology out there is quite late. So not only are you late in terms of capturing this information through your camera feed, you also have to pass this camera feed through some machine learning method out there, which will take some delay. And so there is a lot of delay in behavioral methods. On the other hand, physiological methods that are out there based on EEG, PPG, wearable sensors, so on, they offer early prediction, but it's hard to solve these problems. So I'm going to specifically focus on intent detection. And what I mean by intent detection is to detect the intent to perform a specific action. And in this context, it's braking. Okay. Now, in the context of intent detection, I'm going to focus specifically on physiological methods. And one may question, if you're going to talk about EEG-based methods to do intent detection, EEG usually is a very bulky headset that's out there. And is it even practical to deploy this in the world of transportation? And the answer is the world is actually heading there. So if you look at this particular picture here, this is a patent that is filed by Ford in October 2023. And this is about a helmet that they've designed to collect EEG data while the driver is driving. So transportation industry is actually heading in this direction. And by the way, if you're looking at racing industry, racing has already enforced wearing helmets for drivers, and they're already collecting EEG data today. So to give you the overview, the idea is you collect signals using physiological sensors, you do some level of pre-processing, and then you pass it into some machine learning technique. In the past, you do simple machine learning techniques like which involves feature extraction, feature selection. Modern machine learning approaches use deep learning methods, which basically do both in one go. It's automated. And then whatever comes as output of these machine learning algorithms would be used for classifying or predicting whether or not a driver has an intent to apply brakes, or whether they have whether they are attentive, inattentive, so on and so forth. Now, here is the problem that we have with deep learning approaches. So if you look at deep learning approaches, usually these are very, very complex models. So in order to pass this information, so take the input and process it and get the output at the inference stage, takes a lot of time for that. And it also consumes a lot of energy. So in practice, since we are heading towards electric vehicle adoption today with the growing demand, energy efficiency matters, and deep learning methods are not the ideal way to go forward. So therefore, we are going towards energy efficiency of artificial neural networks. And I think I should set a stage of what we have accomplished so far using artificial intelligence, artificial neural networks using this slide. So here is a simple thought experiment, or it's actually a very nice example that is provided in a paper here in Nature Reviews Physics. And the idea is this. So imagine that you have a total of 1 megawatt hours of energy budget, which is roughly 3.6 gigajoules of energy budget. If you give this energy to a neural network called BERT basically does some simple natural language processing tasks like sentiment analysis and so on. And it has roughly about 10 to the 8 synaptic weights. So that's how many weights that are there in BERT that needs to be trained. So it takes roughly about 80 hours to train BERT using 64 V100 GPUs using 1 megawatt hour of energy. Now, on the other hand, you give the same energy to a human being. A human being's brain has roughly about 10 to the 15 synapses and 10 to the 11 neurons. Not only is this person doing natural language processing tasks, it performs all the biological tasks, everything that is out there, and it uses the same energy for 6 years. So I hope you understand the difference between where we are so far with artificial neural networks and where we could possibly even accomplish, or what evolution has accomplished naturally using biological neural networks. So this particular talk is about trying to fill this gap in some way. And this is not new. This work has been ongoing for a very long time. Learning algorithms and hardware have been co-evolving for quite some time now. And it goes all the way to, development of Hebb's rule and Hodgkin-Huxley's model in the 1950s, all the way to today, where neural networks, spiking neural networks specifically, are co-designed. Algorithms for spiking neural networks are co-designed alongside hardware, specifically neuromorphic hardware. So I'm not going to go into the details. If you're interested, I can share these slides with you. You can contact me later. So let me talk about what spiking neural networks are. So spiking neural networks are simple neural networks which are formed using what is called as spiking neurons. And a spiking neuron is a neuron that is a neuron model that models a change in voltage potential across a cell membrane as the ionic currents flow. So in your brain, if you look at how a neuron works, there are some ionic currents that flow across the cell membrane, and the rate at which this current flows and the consequence is the change in voltage potential. That's modeled using these spiking neuron models. And there are many, many methods out there. So there are many models out there. So Hodgkin and Huxley proposed a model in 1952 for which they won the Nobel Prize too. And even before that, there were very old models called integrate and fire model or leaky integrate and fire model that goes all the way back to early 1900s. So let me show you how this works. Technically speaking, you have a bunch of spike inputs that come. These are Dirac delta spikes that come into the neuron, and you apply some weight. You aggregate all these different spike inputs, and then you pass it through a spiking activation. So this activation function is not the same activation function that you see in traditional neural networks. The output should also be a bunch of spikes. And technically, the manner in which these spikes are processed, the voltage keeps building up as the spikes come in, and there is a threshold after which an output spike is generated. And then the neuron's voltage level goes back to its resting state. And then as the input spikes come in, the voltage value keeps building. So you can see that the model is actually a differential equation. It's not your standard Rosenblatt's perceptron, which is a simple linear combination of inputs. So this is the model of the neuron. And we need to solve the parameters. We need to find the parameters that fit to this neuron model quite well. So one of the first things that we need to do is take the input, convert that into spike values. So if I give you an original image of a car that looks like this, so you can convert that into spike data using some rate coding technique, and you pass this as the input to your neural network. So that's something that you need to remember. Now, understand that once you have spiking neural networks, your traditional backpropagation fails, because if you look at backpropagation, all of the terms, gradient terms, some of these gradient terms actually they do not exist, because you're talking about spike data. So even if you look at a simple spiking activation, or your input, for example, they're all spikes. They're non-differentiable functions, so gradients don't exist. So there are two ways to solve this problem. You either take a gradient and approximate it using some other function to carry out spike-based backpropagation. That's one approach. Or the other approach is to carry out spike timing dependent plasticity, where now the information is not present in the value of the signal, but it is present in the spike timing. So if spikes are more concentrated, there is more information. If spikes are spread far apart in time, then there is less information. That's how you should interpret this as. And the more and more spikes come in, then in a small amount of time, then an output spike is generated, and accordingly, you can decide the weights. Again, I'm not going to delve deeper into the approaches here. That's not my goal. I'm just giving you a broad overview because this is quite a new field by itself. Computationally, these are very hard problems, because you need to solve differential equations. You need to, do backpropagation using approximate techniques, so spike timing dependent plasticity. We don't have really a lot of work out there that gives us efficient methods. Two, on-chip training on neuromorphic hardware currently only allows us to update only the last layer. When you try to do transfer learning, or when you try to do on-chip learning, we tend to update the layers starting from the output all the way to the input. We do backpropagation, and currently you can only do the last layer. You cannot go beyond that, and that's the problem that we have with neuromorphic hardware. Of course, these are issues that are being currently worked on, and I believe that in the next 5 years, all of these problems will be resolved very soon. So that's some overview about spiking neural networks and how you train them. So let me show you what did we do. So the problem that we chose is to detect if there is any braking intent exhibited by the driver based on EEG data that we collected. And we used a 1020 EEG headset provided by Neuroelectrics, NOBO 20 EEG headset. And the idea is the drivers operate what is called as a jetbot. It's a robot that they're operating remotely from some driving station. And we did 3 different experiments here. Experiment 1 is where the driver is provided some audio cues. So there's a countdown, 5, 4, 3, 2, 1, and then they'll be told to stop. And that's when they're supposed to apply brakes. Experiment 2 is they do experiment 1, the same experiment, but in the presence of distraction and fatigue. And what I mean by this is we made drivers run up and down 3 flights of stairs in the middle of the experiment during every few minutes. And then there is distraction, which means they are texting while doing this experiment. So we gave them some text messages. They're supposed to answer some questions, simple math puzzles, and they do this while performing the driving task. And the third experiment is, instead of audio cues, we presented visual cues, just like how you would see on a traditional road with traffic lights. Our first experiment is published in scientific reports very recently. The second and the third experiments are currently under, I mean, we almost have the paper ready. We will probably be submitting it in the next week, in the coming week. So experiment 1. So here is experiment 1. The driver sits, drives the vehicle. So this is JetBot. We have a test bed in our lab. They drive this robot, and the robot has a camera in the front. The camera feed is shown on the screen here. And after some random delay, a countdown begins, 5, 4, 3, 2, 1. And at the end, they hear the audio cue stop. They're expected to apply brakes after they hear the word stop. Now we wait for the next 250 milliseconds, and we observe whether they're applying pressure on the braking pedal or not. And that's all that we are recording. In the process, we're also recording all the EEG data at the same time. So we collected data from 15 participants, 13 of which are male, 2 are female. And then we have roughly about 8 sets of 30 trials each from each participant, with about 5 to 10 minute breaks between sets. That's 240 trials. The total data put together roughly added up to a few gigabytes of data, just to give you the scale of the data that we collected. Okay, so here is what we have observed. So these are averaged out electrode potentials, and here are all the 19 channels that we have collected, and you can very clearly see that right before they hear the word stop, the electrode potentials, the event-related potentials, or ERPs, actually go down and then they come up right before applying the brakes. So specifically, I'm going to look at the CZ potential. CZ is right at the center of your scalp, and you can see that it goes down and then it comes up. So this is a signature that we are trying to detect. Now, here is a scalp plot. So if you look at the scalp plot, initially, a lot of processing goes on, and then suddenly there is a big dip, and then it goes on. Okay, so this is what we have observed. And all we have done is we did not process the entire spectrum. We only processed 0.1 to 1 hertz bandwidth of EEG data, and that's all that we needed to predict whether or not there is driving intent. And there is some simple artifact removal. Artifact removal corresponds to eye blinking and other artifacts which are not necessary here, and we removed all of them using simple signal processing techniques. And finally, we passed all of this into a neural network. So let me show you what the neural network looks like. It's a very simple architecture, 2-layer architecture, 2 convolutional spiking layers. What we have is a leaky integrate and fire model for the neuron, which produce spike outputs as expected. At this point of time, when we were doing this experiment, we did not have access to neuromorphic hardware. So what we have observed is it took a lot of time to train on GPUs. And we used a package called SNN Torch to do this. And of course, the hope was that we would get our hands on neuromorphic hardware very soon for fast training. And by the way, we had our hands on neuromorphic hardware, and we revisited this experiment, which I'll talk about later. So I'm going forward, and we tested this against various state-of-the-art braking intent detectors that are out there. We took a convolutional neural network that has a similar architecture as that of CSNN, just to see what's the difference between CNN and CSNN. And then there is this benchmark called EEG net that's out there that performs quite well. And then there are graph neural networks that are proposed for breaking intent detection. So so here are the results that we have. So if you look at all the other methods, the performance is not that great. I mean, you can see that the traditional CNN or the graph neural networks are quite low, but the EEG net is decent. It's about 97% accurate. But once you get to the spiking neural network, the accuracy goes up to 99.06%. And the same is true with respect to TPR, TNR, F1 score. However you look at it, the performance of spiking neural networks outbeats every other method that is out there. The only downside to this is it has a larger inference time and it takes a lot more time to train, primarily because we don't have the right hardware. All we had was GPU at this point of time. We also did a ablation study. So instead of looking at all the 20 EEG electrodes, we looked at only 5 channels that are right around the center of the scalp. And even then, the performance really did not change much. What we did observe is the CNN started performing quite well. So what this tells you is CNNs, convolutional neural networks, are very, very susceptible to noise. So add a little bit of noise, unnecessary information, and CNNs will start performing very poorly. But if you know which specific channels to pick, then CNN would start performing well. On the other hand, spiking neural networks are absolutely robust to this. They do quite well, irrespective of whether you give all the data in or just 5 channel data. Of course, EEG net's performance deteriorated a bit, which was a bit surprising, but that was the outcome that we had in the first experiment. So it was quite interesting to see that spiking neural networks with just 2 layers can outbeat all the standard benchmarks that are out there. Not only that, you can change the threshold in the spiking activation in the architecture. And as we change the threshold, this is the delta modulated spike train input, meaning, so you take the spike, you take the real valued data as the input, and then you apply a threshold to it, you generate a spike. So this is the threshold. You can see that the accuracy really doesn't change much, even though you change the threshold from 0 to 1. So 0 and 1 are the extreme values. And these are really, really extreme changes. And in spite of that, the accuracy, it doesn't affect accuracy as much. And that's true not just with respect to accuracy, in terms of TPR, TNR as well. So, so that's good news. So spiking neural networks work, at least in the context of breaking intent detection. So let's move on to the next experiment, because in practice, in the real world, drivers don't really drive under normal conditions. They're always distracted. Maybe they're fatigued. So we wanted to see how this system works, how this algorithm works, model works under such conditions. So we did the same experiment. This time we had 11 participants. We collected 5 sets of 30 trials each, again with 5 to 10 minute breaks in between. And during these breaks, we made them run 3 flights of stairs. And we also made participants answer text messages while they are doing this experiment. And totally, we have 150 trials. Again, a few gigabytes of data is what we collected. The architecture is exactly the same as CSNN that we developed in experiment 1. So just to show you how the scalp plots look like, I'm going to focus only on this side because this is much more easy to follow. But you have all the 20 electrode data to the left. So if you focus on what's happening, this is the case when you have ideal conditions. So this is experiment 1. So again, there is a clear dip right before they wanted to apply brakes. And once they hear the word stop, you see an improvement. You see a similar signature here as well. The only difference is that they're extremely distracted while they are doing this. Fatigue did not play much of a role. This is what we have observed. It's a distraction that played much of a role in performance deterioration. And you can very clearly see, in fact, to such a detail that So when you see an activity at the very back of the brain, that means they're looking at a question on the screen, and then they're processing what to answer to that question. And you can see that this right part of the brain is extremely activated, and that's because that portion corresponds to the fingertips of your hand. So they are actually texting while they are applying brakes. So the braking intent is right at the center, at the CZ point, but you can also see that they're heavily distracted by the texting here. So this is what we have observed. And by this time, luckily, we also had a neuromorphic hardware in our hands. What we had was BrainChip's Akida ADK 1000 processor, which has about 80 neural processing units, and which support 1.2 million neurons and 10 billion synapses. So that's the capability of this neuromorphic hardware. And to compare against, we used one of the CPUs that we have in our lab workstation, which is a Xeon W2123 processor with 32 gigabytes of RAM. So the idea is as follows. The methodology is as follows. We first trained a simple CNN model that looks exactly like our CSNN model. We trained it on CPU on all the three data sets, and then we quantize the weights. So the weights were real valued weights when we were training using CNNs on CPU. Then we apply quantization on weights, and after that we modify the activation functions into spiking activation functions to convert our architecture into CSNN. And then we pushed that into Akida. We did on-chip learning on some extra data. So the data that we used for training in the initial phase was 8 out of 11 drivers. On-chip learning with 3 out of 11 drivers. So this is how we split the data. And what did we get? So here is the results. Now, initially, when you look at CNN, the accuracy was quite high. Once you quantize, the accuracy dropped a little bit. And then when you push it into Akida, the accuracy dropped quite significantly. And when we do edge training, on-chip training on Akida, again, the accuracy goes up quite a bit. The same story applies even to TPR-TNR as well. Now, that's not the end of the story. So you do get good performance on Akida. But the story is as follows. Akida, if you look at the amount of energy for one single inference run, that's almost like more than 50 or less than 50 times the energy that it takes to run the architecture on a CPU. So we are actually having some 50 times energy savings by using CSNN on Akida as opposed to CNN on CPU. This is the gain that you get by adopting spiking neural networks or neuromorphic hardware. Do you see any gain in terms of inference time? Our observation is that there is no much gain in terms of inference time currently, but we assume, or we predict, at least our conjecture is that as neuromorphic hardware gets better over time in the next 5 years, we will also see a significant improvement in terms of inference time too. But we already see quite a big improvement in terms of runtime, in terms of inference energy with Akida CSNN on Akida. Not only that, you actually can do this training much quickly. So for example, if you look at Akida edge training, it only takes 1 epoch to get to 90% accuracy. But on CPU, if you use ADAM algorithm, it takes roughly 4.5 epochs. So it takes a lot more time to do edge learning or on-chip learning with traditional neural network architectures. But with spiking neural networks on neuromorphic hardware, we have few-shot learning. So that is the outcome that we have with experiment 2. So then the next question was, what about visual cues? Because you don't really see audio cues in practice. You get to see visual cues in practice. Traffic lights is what we see. So we did the same experiment again. We made drivers drive around a block, and we put traffic lights on 2 corners of the block. we particularly told the participants to ignore the traffic light on this corner, but to stop whenever they see a red light here. So if they see a red light here, they should just ignore and go. But if they see a red light here, they should stop. So that was and these these lights were changed randomly. There is no specific pattern here. Now, again, the experiment was done using 11 participants. 3 sets of 30 trials data were collected with 5 to 10 minute breaks. Totally 90 trials, quite a bit of data. And participants were given visual cues, traffic lights, without distraction and fatigue. So there was no distraction in this experiment. The same architecture was used as discussed in experiments E1 and E2. And you can see that here is the signal that you would see in the presence of, this is experiment 1 signal, again, EEG signature under audio cues. Under visual cues, we also have a very similar signature. So CZ is the third signal that is here. So left side picture corresponds to when they are applying brakes. The right side picture corresponds to when they do not apply brakes. So you can see that when they apply brakes, the CZ potential again takes a dip, right, when they see this red sign. So this red line here corresponds to when they see the red light. Yellow line corresponds to when they see the yellow light. Otherwise, it's green all the time. So you can see that once they see the red light, the CZ potential goes down and then it comes up. But if they are not applying brakes, you can see that the CZ potential is pretty much flat. That doesn't change. So I hope that, so in other words, we are looking at the same signature as what you would see with audio cues. So here are the results with experiment 3. Now the results are, we have again very good performance with convolutional neural networks at the beginning, and then when we quantize, there is a slight performance drop. When we convert the activation functions into spiking activation, the performance dropped even significantly. But when we do edge learning, performance again improved quite drastically. I mean, this is a bit of a very idealistic performance to see. We don't expect this when we have more data in our hands. But nevertheless, CSNN took very little energy, again, 50 times, roughly the energy of 40 times or 50 times the energy improvement in terms of when we use CSNN on Akida as opposed to CNN with CPU. Not much of a difference in terms of inference time. So the gain is in terms of energy consumption. Also, if you look at the edge learning, we have few shot learning again. Within 2 epochs, we were able to get to 90% accuracy on CSN and Akida. But with CNN CPU, we need to wait for 28 epochs to get to this. So it was not really a great. And by the way, all these numbers in the brackets are standard deviation. So these are, we did a cross validation over multiple drivers, and so that's the standard deviation that we get here. So you can see that CSNN Akida is much more stable. With fewer epochs, you can get to 90% accuracy very quickly. But with CNN, it's not really that accurate, and it's not very stable as well. So let me conclude. So these are our results. So let me conclude my talk with the following claims that I'm making based on the results that we had. The claim is that convolutional spiking neural networks significantly outperform state-of-the-art graph neural networks, graph convolutional networks, or graph convolutional spiking with skip connections here for EEG-based intent detection. And not only that, practical demonstrations on neuromorphic chipsets for other experiments in the literature also shows tremendous energy savings and extreme fast on-chip training time for model personalization. So we were able to do model personalization in our approach. So when we say that we were doing this edge learning is for individual drivers. So we were personalizing these models for each individual driver. And that's what we mean by model personalization. So what are we doing now? There's a lot of ongoing work that's happening. There is some future work that we already planned. So currently we are looking at neural correlate models for intent detection. We are trying to understand how the workload is on the drivers. For that, we are using independent component analysis on different bands. And we are also using Pearson correlation coefficients between various sources in the brain. So this independent component analysis effectively does source separation. When you look at inputs coming from EEG electrodes, the actual signal that we receive here comes from various sources. So we are separating those sources and we are trying to do some correlation studies here. And that's what we mean by neural correlates. And that's our goal that's how we are trying to study the driver's cognitive state in a much more deeper manner. We are also trying to do a multi-model breaking intent detector. We actually have EEG plus ECG, EEG plus PPG experiments planned out for fall. We are looking for, we are planning something in the long term for an experiment with EEG and FNIRS, but we don't have our FNIR set yet, so which is why we're waiting on that. We're also looking at neurofeedback design, meaning once you understand that a person is inattentive, naturally you need to perform some sort of a feedback. One approach to give feedback is to give a neurofeedback, and that a simple example could be to play music. So to play the right kind of music or noise in the background to help improve people's attention. And that is something that we are looking into as well. That's planned out for the next couple of years. We have a grant going on that. And some work that we have done in the past, which is related to this, which is not based on intent detection, but based on shared control intervention, is to model drivers as open quantum cognition models. So we used quantum physics models out there to model driver behavior, and it works quite well to our surprise. And we developed some shared control interventions using game theory. And so that's some related work that we have done, which I'm not going to talk about, which I'm not planning to talk about today. So if you're interested, talk to me offline and I'll be happy to interact with you. So that's pretty much what I have. So thank you for this opportunity. I'm going to leave the next few minutes for questions. But we are always on the lookout for passionate and self-motivated students who are interested in trustworthy cyber-physical systems. We dabble on problems in machine learning, game theory, algorithmic fairness, and cybersecurity. So here is my contact details. So I leave the floor open to questions.
Thank you very much for your presentation, dear Dr. Nadendla. I'd like to ask one question, if it's okay for you. I'd like to just point at the trustworthy design. I mean, what do you think about that human error that may be alive in the data we are using for that? I mean, the training purposes, maybe on the background. Of course, we are supposed to be using that EEG data instantly in real time. Maybe we have some data science-oriented, some precautions, of course, methodologies. But what do you think about for the future? I mean, the human errors will human errors be exponentially increasing in terms of the data to be training that spiking neural networks, for example, and would it be being a more critical issue when we design some more agent-based systems? So what do you think about how to deal with the human error, or would it be possible to solve such problems thanks to such that the design that you mentioned with the existence of the human in the system structure? Yeah, my question.
Right. So I mean, I don't completely understand the question because
maybe I can add some
yes.
thing. Hey, what and how is it susceptible to noise? And what about the spike timing? I think I wonder whether is it this so-called spike neural networks, are they
Right.
sensitive to noise? If so, how do you model that in your training? That's my first question, and I think that's kind of a similar thing from Woodku also.
Yeah. Human error means noise or
Go ahead.
outliers. Yeah. Sorry.
So let me go back to a table which I might have gone through very quickly. So if you notice what's happening here, so you take a real value input and you compare it to a threshold and you convert that into spike, which means even if you change the real valued input by a small value, that as long as it is greater than the threshold or less than the threshold, there is a noise margin present within the system design itself, which naturally introduces resilience to noise. So this is the example this is the study that we did. You change the threshold. Even if you change the threshold quite drastically, there is not much of so 97% to 90% accuracy. Yes, it is a drop, but it's not a big drop. So it is quite resilient to noise.
When you refer a thresholds is actually the magnitude of the spikes or the threshold or for your algorithm to.
No. Spikes are always of constant magnitude. So if you look at EEG data, these are real valued electrode potentials that you're getting. So you compare that to a threshold and then you convert that into spike data. So if the EEG value increases beyond, let's say, 0.5, then you convert. So these are normalized. So we converted EEG data into normalized EEG data and then apply, let's say, 0.5 threshold. If the value is beyond 0.5, you have a spike. If the value is below 0.5, there is no spike. Similarly, if you change the threshold value to 0.25, if the value is greater than 0.25, there is a spike. If the value is less than 0.25, there is no spike. So that is the spike coding that we did. And once you have these spike trains, so you take the real valued EEG input, convert that into spike trains, and these spike trains are provided as inputs to the spiking neural network. And that neural network's performance really did not change in spite of changing the threshold. So in other words, it's quite robust to noise in general. And that's what we have observed in our experiments. And not only that, I mean, I'll give you another example where we looked at a different kind of noise. That's experiment 2. The experiment 2 is where you have distraction and fatigue. So the person himself is undergoing a lot of distraction. They're supposed to answer text messages. They're tired because they're making them run 3 flights of stairs between breaks. So during one round of experiment, they would have at least run 3 flights of stairs thrice. And with such an amount of distraction, so you can see that these brain maps look very different now. So there is a lot of overload on the people's minds as they're doing this experiment. But still, spiking neural networks are extremely good at handling all of these issues.
How realistic these distractions are modeled when looking at in a real world driving scenario? For example, it's a complex mapping when you really want. Imagine that you have you're driving, you have a lot of parallel things. Your cognitive thing needs to look into for situation awareness.
Right.
And you are modeling in terms of fatigue and distractions using stairs. So how do you map that? How do we ensure the distractions is indeed you will get similar curves? I'm just curious to see what your thought on that.
Right. So fatigue, at least whatever experiment that we did, it had no impact on the results. So 3 flights of stairs had no impact on drivers' driving ability. I think we need to make them run more or make them do a lot more heavy-handed work to get them tired. On the other hand, distraction, texting while driving is quite common. In fact, that is exactly how I started off the talk. So let me show you that one of the factors, so you can see the distraction, phone, talking, eating. So you have a lot of distraction that's causing fatalities. And texting is one of the very well documented, concerns that.
Are they doing two different tasks when you are doing simulating in your lab? They're just texting, but what else are they doing? They're also doing multiple tasks in your lab setting. I'm curious to.
No, we controlled the experiment quite a bit. So it's just texting. Maybe they'll be talking to the supervisor who is managing the experiment, which is the student who is managing the experiment. And then they would be driving. So this is a controlled experiment in that way, Prakash. So
how would this would change when you want to replace EEG with MEG or fMRI or NIRS, to see, in a control setting, I wonder whether how those signatures from those other types of sensors, which may provide high temporal resolutions, similar to EEG, have you looked into, looking at that for detecting blood flow or tracking different things?
right. So we don't have the other sensors yet. So we don't have an answer to that, but the expectation is that we would be able to study what's happening in the brain more spatially at a higher resolution. Temporally, the spatiotemporal analysis of the brain during this experiment is something that would give us more insight into the workload, the driver workload, and and how distraction and fatigue and all these factors impact their ability. We are planning something similar in fall, and not in the context of driving, but we have another experiment where we are asking participants to do letter and back, flanker and back. We also have an experiment on drone flying with distraction and so on. So there we have multimodal data coming in, but that's planned for fall. Currently, we don't have anything yet. But yes, we are also looking for an answer to the question that you posed.
And I may have missed it. Maybe you mentioned this. Okay, eye tracking. Are you looking at some frequencies for visual cues? Are you also looking at other types of visual approaches?
Right now, we are not doing that. In fact, we can have artifacts about eye blinks and all in the EEG data set itself. We removed all of them. So if I go back to, so we have this artifact removal block going on, which removes all those artifacts from our data. But it might be something to consider. At this point, we are not looking into that, because these are eye blinking and all on EEG data can introduce a lot of noise. So our next step, in fact, I have a student who is looking at automating all of this, integrating all of this into the neural network itself. So why go through all of this? Because this requires a lot of offline processing. And so currently our method is not truly an online method because of pre-processing steps. So we are, in fact, my student is developing a generative adversarial network to a generator to automatically clean all the artifacts and noise, and then send that denoise signal into neural network straight in one go. So that's.
I have another question. Thank you. When you talked about the proposed approach with the two-stage or this on-chip learning, could you help me understand a couple of things? For example, you mentioned 3 and 11 drivers, right? And do you have a different age groups of drivers in these emulation that you conducted, or it's a very small pool of drivers? I was wondering whether you considered distribution of age or gender in terms of.
We did. I don't have that demographic information here. So we had mostly there were students. I have to agree on that, but we did consider some level of diversity in terms of race, in terms of gender. We had students from different backgrounds. We also had staff and faculty participating in this experiment. So at least there is one faculty member in 60s one in their mid-30s, which is myself. And then we have staff members in their 40s, mid-40s. So they're included in this experiment. So it's not a lot of pool,
Yeah.
but again, that's what we could do.
What is your vision for using the edge learning? You're thinking something that resides within the vehicle that will compute something at some point. What is your the
Right.
edge?
So the vision, the vision is we have this model that is trained on group data. So that's this initial training phase where we would have, or maybe even on chip. Yeah. Think of it like the initial training phase is a model that gives you a group average model that works generally well for a population. But then when you actually deploy it, you want to further fine tune it for the individual driver who's using the car. So we introduce this edge learning component to fine tune the model for that specific individual driver. And our assumption was all we have is a few seconds to quickly learn what the driver's workload is, and then fine tune it to the driver, and then have this model, this fine tuned model, predict personalized intent for the drivers. And then when a driver switch happens, in practice, a car can be shared by multiple drivers. I mean, if you're in a family, you tend to have multiple drivers using the same vehicle. So then the car would automatically revert back to the group average model and then very quickly learn what the new driver's conditions are and then perform. So that's the vision that we have. So this on-chip learning is more like a personalization module that's there in the car. And the plan is to use Akida. Akida is literally the chipset is the size of our palm. It doesn't take much energy, so you can easily connect it in a car today. So that's how we are envisioning this.
Thank you. Utku, do you see any other questions on the chat or anything?
I'm not seeing, but I'd like to ask about that. What do you think about the open gaps challenges for the spiking neural networks? That's my last question.
So again, there is a lot of work that needs to be done both at the algorithmic and the hardware level. So one of the things that we have with spiking neural networks is you really need neuromorphic hardware to see the gains of, and the neuromorphic hardware that we have today only allows us to train the last layer. So even the edge learning method that we have, it's only tweaking the last layer. It's not really training the inner layers of the architecture. Imagine what we could do if we have the capability to train the inner layers too during that on-chip training phase. So we don't have the capabilities right now.
Yeah,
not just my lab, but no one in the world has that ability because the spiking neural networks, theoretically, they can support many operations. You don't necessarily have to have a feed-forward architecture. You can have any kind of graphical support on spiking neural networks. But hardware doesn't do that. It all boils down to how they're working on them. So,
Yeah.
and algorithmically, we also need faster algorithms for training. That co-evolves with the hardware. So there's a lot of nice activity in the field.
Thank you, Dr. Sid, for taking the time to do this webinar for us. I think it's interesting and to know your significant piece of work that you happen to share during the webinar. And as part of your time, UND will send a nice plaque and certificate from our dean for your contribution to this webinar series. I hope we can able to work in future in some kind of form of collaborations. Especially I see some opportunity, the edge test bed that we have, and
Right.
I think thank you so much for your time, Sid.
Thank you, Prakash,
Thank you
and
very
thank
much.
you. This is a wonderful opportunity that you have given, and I'm looking forward to collaborating with you all. So,
Yeah, sounds good.
Always.
Thank you.
Thank
Take
you.
care. You have a happy 4th of July.
you too.
Thank you.
See you.